So the way that we can use these little tubes or filters, either in groundwater remediation, that means that if we want to target where the contamination actually is underground, we can do that through this technology. So we can scale up our system, put it in the ground, circulate the water through it, and in that way treat the groundwater. Thank you, everybody, for coming today, and I really want to thank organizers. I think these kinds of events are really of great importance for us scientists and for everybody to hear what we are doing in our labs, so it doesn't just stay there. So my name is Lily, and you can refer to me as Lily, and I'm a chemist by training, as Daryl mentioned, but my research more focuses on environmental engineering, and more specifically on water treatment systems. So I was thinking how to start, because water issues are so broad and complex, and giving you numbers and statistics I don't think would relate to you as it would if you reflect on your own actions throughout the day where you use water. And I like to think about it as I wake up in the morning, what are the things that I do throughout the day where I directly use water or indirectly use water. And some of the examples you can think of: first thing in the morning, you just put probably your coffee on and do a bathroom routine and fill the water bowl for your dog maybe, and all those things require that you directly use water. And we didn't even reach 7:30 probably in the morning, right? Then there is another set of different things and actions throughout the day where we use water indirectly, and where it's really hard to grasp that because it's not in front of you. For example, our mobile phones, almost every part of mobile phone is made, or in some point in process, uses water for its production. So if you think about it, there's a lot of water use for the amounts that of technology that we use these days. And if you can imagine that as all those things happen, water quality as it was at the beginning, after you use it in any way, either directly or indirectly, it changes its quality, right? So it's not anymore the same way as it was. Unfortunately, that usually means that water now has certain contamination. If you brush your teeth, now it has toothpaste in it. If you showered, now it has shower gel in it. If it was for metal processing, now it has a bunch of other stuff in the water. And unfortunately, nature is not capable of cleaning all of that waste for us. And unfortunately, it reached back to us actually through water cycle. So thinking in those terms, and then thinking that if we start from us, how much we impact as individuals on water quality, and then if you think of all of us here do the same, and then everybody in Copley Square, and then everybody in Boston, Massachusetts, US, if we want to stop in US, that's a tremendous amount of burden that water quality suffers from different actions that we have throughout the day. That sometimes, for me, makes me feel anxious and depressed, but I channel that into a question: what can I do about it? And that's my main motivation for research that I actually do. And what I actually do, since I started my PhD, I introduce electrochemistry, which is basically using electricity to treat water. It can also be implemented for sediments or soils and other environmental media that can have contamination. And it's actually a really simple principle. Using electrodes, which are any materials that are conductive and not potentially can release anything toxic into water or soil, we can use as electrodes, and by forcing current or electrons to flow through the system, there are different reactions that can happen that can help us degrade a wide range of chemicals that can be present in the water. Currently, there are a lot of treatments that can be used that are very efficient for water treatment, but they require a lot of maintenance usually. You have to add certain chemicals to degrade chemicals. And that requires a lot of transportation of chemicals, production, handling, and adding those chemicals in certain periods of time. So it's not as sustainable as it should be and it can be. So electrochemistry, because it's so flexible, and by turning the current on and off, you basically control the system, it's much more flexible, much more scalable approach than other systems can be. One of the important things, I think, is that as, for example, solar power is getting more and more accessible, and solar panels are more and more cheap every day. Whenever I checked, it's at least $10 less. So that is another very important aspect of introducing electrochemistry for environmental engineering, where we can rely on these alternative power sources. And that can be applicable not just in developed countries, but also in developing countries. I just gave you this. It's really small, a lot of reactions there, just to give you a glance of, these are all different reactions and different chemicals that we can treat with our system that we developed at Northeastern University. And they use basically similar electrodes. It's just the way that we organize them, how we distribute the current with little electrical devices that are really cheap and affordable. We can degrade different kinds of contamination, starting from heavy metals. We can't degrade them, but we can transform them in a way that they are not harmful anymore. And we can actually degrade certain organic compounds. When I say organic compounds, I mean, let's say, pharmaceuticals that are unfortunately in our water, chlorinated solvents that are used widely in industry, pesticides that come in water through agricultural activities, and things like that. So it's a really wide range of application that we can do with this kind of technology, and we can really vary what we want to accomplish fairly easily. However, I don't know how much you see, but our main process, which is called oxidation, is something that we are really focused on in our systems, relied on palladium catalyst. What that means is that's a noble metal, works great, help us create certain conditions, but you can imagine how expensive that is, right? So in thinking, treating larger volumes of water, and in different countries throughout the world where monthly salaries are as 1 gram of palladium, we can't introduce technology like this. So we were looking more, how can we improve, either maintain or even better improve our systems by not using these noble metals and very intensive materials in terms of costs and amounts that we need to use. So I just wanted to give you a glance of how we test this system in our lab. So we have basically, I will show you here, these little reactors. They're, I can move so you can take a photo. They're basically tubes where we implement certain array of electrodes inside. The first one is, I call it Frankenstein 1. It's a version 1, what we started from, and now we improved it into this better version that is much easier to manipulate with. So the way that we can use these little tubes or filters, either in groundwater remediation, that means that if we want to target where the contamination actually is underground, we can do that through this technology. So we can scale up our system, put it in the ground, circulate the water through it, and in that way treat the groundwater. All system will be solar powered, and it is at this point. This is an example, I don't know if any of you use small drinking water systems in your house, or have you ever seen those RO units and filters? So they usually have, in order to be really, really efficient, they usually have a couple of filters connected to each other. What we envision is that with our technology, we can have one in all, or all in one, sorry, not one in all. Of course, more research is needed to be done for optimizing a system like that, but there is a really great capability to combine different treatments in just one system. So would you like to have that in your house? Is that something that you would be happy with? Just have one filter and don't think about water for 2 years and maintaining it or thinking about changing anything. Because at least currently, whenever I talked with those who do have water filtration systems in their households, for example, you have to worry about changing the filters every 6 months. Sometimes it's not even just it costs a certain amount of money, but it's just a hustle of thinking about it and ordering things, and we are kind of spoiled in a way and want to get things easier. So this is, you can probably recognize, this is a rooftop of our building at Northeastern, where we tried our solar panels and to see how, if we can make them work in Boston in fall, there probably will be a good source of energy for other places. And they actually worked pretty well, which I was really very happy about. That's we call it pilot scale. It's a little bit bigger amount of water, larger amount of water that we can treat. Mighty carbon. So why I'm saying that is because carbon materials are really now used and have been used in a lot of water treatment systems, and new ways are introduced more and more how we can use carbon materials in this case. And if you remember, I mentioned we used that palladium that we wanted to get away from. Carbon is something that we now introduce in our systems instead of palladium for a couple of reasons. It's way cheaper. It can be produced from waste, so we can definitely minimize the impact on environment from other materials that we would potentially use. So there are different varieties and forms of carbon that exist now that you can buy, so they're commercially available, very, very cheap, accessible, and in different forms and shapes. Some of these worked 10 times better than the palladium that we initially thought it was a very efficient treatment method. Now with the carbon materials, we can accomplish even more. So we can use it because it's conductive, so any conductive material can be used as electrode, but of course we don't want to use materials that can potentially be even more toxic than what we're trying to remove. It's a really low cost, low carbon footprint, and why I said high flow rates, you don't want to wait 1 day for 1 glass of water, right? So we want to improve the treatment of of water with these filters so they can be in real time. As you open your tap, for example, you can have clean water under the flows that you want, because those are demands that we need. So why is this innovative? Many research groups do look into these materials. Our innovative way of introducing these systems is that we don't add anything outside the electrodes and power. So no addition of chemicals, no addition of extra oxygen, hydrogen, any of the other materials needed for the reactions that we want. So that's a power of electrochemistry, where we can manipulate system just by current. So that is about my water-related research. I would love to talk with you a little bit more about what kind of questions you might have or concerns with this, or what is not clear, maybe how is this different, why carbon, why electrochemistry, and any kinds of questions that you might have. Yes? Yes.
Hi, I've got a couple of questions. One relates to the potential for using this technology for remediating groundwater from fracking. You know, there's political problems in that chemicals are proprietorially protected and things. But I'm Australian, as you can probably hear, and our Great Artesian Basin is a non-renewable source of groundwater which is being depleted and poisoned by fracking. And I was wondering, would it be possible to put one of your wonderful instruments into the ground and do some good with it?
Potentially, sorry. Yeah, thank you for that question. Everybody heard the question? So potentially, yes, that can be a possible way to do it. The one thing that is a little bit tricky with it is that we need to know what is in that water. So analyzing if it's a company that does that legal-wise, we would have to first know what is there and do a sampling of water and test it first. So that's the thing with fracking. There's a lot of salts and other things that we don't necessarily know are added into how they do the fracking into those solutions. So theoretically and scientifically, yes, but practically, I'm at this point I can't tell if it's doable. Yeah. Yeah, it's kind of tricky with those confidentiality of the firms usually don't have to disclose what they're using. So if we want to dig deeper and do the more in-depth analysis, I don't know if that would conflict with any of that. Yeah, because some of those are not still regulated, I think. So that's tricky. Yeah, hopefully there is some solution soon. Yeah. Okay. Yeah, you can. Oh no. Is anybody else have any questions? Or yes.
Hi, thank you so much for your presentation. I was wondering if you could talk a little bit more about how your system can help with heavy metals, specifically if you look at Flint, Michigan, and there's a lot of lead, if it could help with that, or even mercury or any other arsenic, perhaps.
Thank you. Yeah, so in the past, we did some experiments and applied this technology for removal of heavy metals with a little bit different approach. Using its process called electrocoagulation. So it's basically settling down heavy metals. That's very efficient, but it has a lot of precipitation after that treatment. It's doable to do that, and electrocoagulation has been applied for that. There are other we didn't test for mercury, for example, but arsenic can be removed definitely with this type of system.
Just a follow-up question with that. Practically, is it something that a city would need to implement, or does it need to be done on a smaller scale, individual home level?
So in this stage of our work, to have certification for these filters to be implemented in homes, it takes some time. So 5 years from now, I think we will have these in the market. Otherwise, technology has to be approved for either a remediation purpose or for household use. It has to be approved. So that usually takes some time to get to that point. Yeah. So we are still in the scale of moving a little bit further than proof of concept. Yeah.
I just came in, but I wanted to know about fuel cells and using wastewater treatment for methane to using the fuel cell to produce clean water. This might not be a subject.
I'm not an expert in that. I think there is a lot of research done in microbial fuel cells, and there's a lot of potential in that area, but I can't speak too much about it. Yeah. No, that's a great question, though. Yeah.
Hi. Yeah, the second question was that microplastics are ubiquitous. They fall in the rain. They're in my water that I'm drinking and tap water and things. Now, I think some of the concern around those is that that they can release chemicals, which I'm guessing would make them amenable to your process. But what other ways can your process help with kind of microplastics? Because we're sort of plasticizing ourselves apparently, and it can't be good for you.
That's a really good question, and I didn't think about. I think. Give me a second. At this point, I'm not sure if we could do the treatment of those kind of chemicals. Yeah, I don't. We never tested it, so I think so. Yeah, I think so. So our focus so far was mostly on all those chlorinated compounds that are really ubiquitous in a lot of groundwater throughout U.S. And all of Superfund sites. I don't know how much you are knowledgeable of that, but they're in 90% even more, and they're carcinogenous. And so our focus was mostly on those contaminants, and now expanding to pharmaceuticals and pesticides that are, especially pharmaceuticals, in really low concentrations that is really hard to degrade, sometimes analyze, even them as a parent compounds, and throughout the degradation, what is actually happening with them is also something that in treatment, water treatment is a very big issue. If you sometimes can even, unfortunately, make something that's even worse than what you start from. So that's something that we are looking into more, expanding from those chlorinated compounds to expand on those chemicals of concern. Yeah.
You just mentioned Superfund sites, and it reminded me of something. Did they ever go back? Because a lot of the Superfund sites were cleaned up many years ago before a lot of new science was developed. Do they ever go back and look at them? I'm specifically thinking of the one on the Arsenal, near the Arsenal Mall.
I think there is certain, I think 5 years after there is a monitoring of the site after they close it. So that would be as far as the monitoring would go. Usually those treatments do last so long that even with very efficient technologies, unfortunately. But yeah, going back is to a certain point. There are so many sites that are on a national priority list that are not even started being remediated. So I think that kind of is a priority, and then going back is something that is set for a certain amount of time.
I'm just wondering, what is the time frame it takes for the current device you have in producing, like, say, a gallon of clean water or something along the lines of that?
Thanks. Yeah, that's a great question. So at this point, we can treat under flows that are much lower than your faucet, for example, flow is. It's like 2-point-something gallons per minute. We can treat 10 times of that. Less at this point. So that is one of the goals that with these new electrodes, we are trying to increase the volumes that we can treat with this technology much more efficiently. Yeah. The good thing is that although the system uses electricity, even if it's not hooked to a solar power, the amount of power that is needed is less than a light bulb. 4 times less. So those are really low currents that we use. So that kind of lowers the impact on the environment, as well as the price that you will have to, the cost of the treatment you would have to pay.
Thank you. I was just wondering, as far as the applications for this type of water remediation, this was touched on a little bit earlier. You know, there could be residential applications, but with your, talk of different types of flow rates, could this be actually introduced into a natural environment that has contaminations, and kind of, what are your thoughts on that?
Thank Thank you. Yeah. So treating groundwater is the application that you're referring to, and there are different ways that these systems can be implemented in the wells, groundwater, wherever the contamination is, through recirculation from the well to the system. We can do applications like that. And the good thing is that we can do that in remote areas by using solar power and not disturbing as much the surrounding areas of wherever the site is. I hope I answered your question.
So thank you. You mentioned using this in wells. You know, if there was somewhere that maybe had some wildlife or there's kind of microbial, you know, activity, how would the electrodes kind of, you know, work in that sort of environment? Is that a constraint at all?
So I don't see this be running anywhere where there is life of some sort. Microbes, if they're pathogens, we actually are aiming to inactivate them with this technology. So it's a good outcome. But I wouldn't envision this to be used in a system like where there is certain life of that sort. Yeah.
I was just wondering if your system works better on chemicals that are lipophilic or lipophobic, or if there's a difference.
Thanks for that. So there, introducing carbon as electrode is actually giving us more flexibility in types of chemicals we can degrade, because carbon tends to absorb hydrophobic substances, so that will help their removal in addition to electrochemical processes. The other hydrophobic and substances that are to a certain level dissolved in water, those are the ones that we can definitely treat with this system, and as we do.
You had mentioned before that a normal filter needs to be changed like every 6 months or so. With this technology, how often, like what is the life cycle of it, or does it need maintenance often, or whatever?
Okay, thanks. Thank you. Yeah, that's a great question. The beauty of electrochemical systems is that there are tiny little electrical devices that can help us clean the electrodes. We can program that. They're called programmable devices or polarity reversal devices that can help us actually clean the electrodes to a certain point. So it wouldn't be the same as you would have to replace the carbon filter every 6 months. It would be a year, for example. So, and you wouldn't have to do that. So you can just program the little device to do the cleaning for you. Yeah.
Could you talk a little bit more about, you know, how you got into this field of study and why this is so important to you?
Sure. I would love to talk about that. Thanks for that question. So I grew up in Serbia, in Eastern Europe, and we don't have any regulations at all. And there is a lot of contaminated streams, air as well. And me as a chemist, when I was finishing my bachelor's degree, I realized that as a chemist, there are a couple of career paths I can follow that were kind of what people usually do. You go either doing analytics, or you would go to pharma, and that's kind of it, like doing some biotech maybe. But I really wanted to do something about that. Surrounding that, I noticed that it's really bad. The industries, for example, they were just dumping wastewater without any treatment. So I figured that, yeah, I want to use my chemistry knowledge and love to chemistry to actually not produce those chemicals, but to do something about them. And that was my main motivation to do PhD at first place, and then join that program that was funded to do sediment treatment. So that was kind of how I from a chemist went to actually environmental engineering later on in my studies, and I never regret it. yeah. So that's that. The other thing I really am enjoying a lot, and I think it's really important for us to put efforts into, is education, starting from earlier age. I don't think there is any change can happen if we don't do that. So my career kind of also has that path of introducing students of younger age to do projects related to environmental protection and just learning, just not even understanding electrochemistry, doesn't matter. It's more of thinking in terms of concepts and how you solve problems and how to implement that one day as an engineer. So those are my two passions.
You started off to bring it home to us from the individual perspective, and I'm sure we're here all recyclers and things like that, but to what extent is this a systemic problem, and to what extent can your solution be a systemic solution, I guess?
All those issues are really systemic issues, and I think we have to start from us, whatever we do, but that is also a tip of the iceberg, I think, if we say. I think the most changes that would influence how the environment is and will be is corporations and how they handle their production processes, because that is where things start, at least in terms of contamination of water. The products we use, how they are produced, and all that has to be in a much better place.
Does anyone have any other questions? Last time I asked this, someone had another question after I concluded, so. All right, and this is your last chance. This will never happen again. All right. There we go.
I wonder about when you talk about personal, maybe too expensive or complex to be scaled down to individual homes right now, but personal response is how have you tried to integrate any of this technology as a community basis, and sort of what the response is when you talk about cutting edge technology and some of the fear that comes around this sort of futuristic tech, how well it's received or not received or wanted in communities that have serious contamination water issues, but is this considered something that's scary or wanted, or how does that play out?
Well, at this point, thank you for that. That's a great question. At this point, we didn't do that kind of interaction, but through the center that we have at Northeastern, we do have a community engagement core that handles all that interaction with our participants, for example. So in thinking those terms, once we are moving forward with the technology, we'll definitely work with social scientists to actually learn how to interact and how to implement this in the best possible way so they understand what that is. Yeah.
What do you envision the future of clean water to look like?
Okay, that's a tough one. As I mentioned previously, I think that in order to make bigger changes other than just us thinking in our own homes, there has to be changes in industries for sure, and thinking more sustainable in those terms, and putting in place better regulations that can protect not just water but other environmental media as well. I think that's the only way to actually make bigger changes. We can do as much as individuals, but bigger changes will have to follow that path. Yeah.
Said, what can we do as consumers or individuals that would help?
There's a lot of things we can do, but those are really lower scale, if you think about it. In terms of, for example, quantities of water that we use, we can definitely not take like long showers every day and things like that. But really, the amounts of water that industries are using are such a tremendously higher that it's not even comparable. The only thing that us as consumers is how much of our demand drives that industrial progress is how much you actually use of products that contain certain chemicals, and but that's also thinking about your own health, right? So it's not just like what you used to be finally enter the environment, but exposing yourself as well. So I think that us as individuals, we can do a lot, but bigger change need to happen from bigger systems.
All right, thank you so much. Oh, one other question. This is exactly what happened last time.
I was wondering if this technology or a version of it could also at some point be applied for saltwater purposes, just thinking of all the contamination in, say, our oceans.
Thank you. So this technology or similar application is at least research at this point to protect saltwater intrusion into groundwater. So that is one of the applications that has a great potential. The other issue with saltwater is it has chlorides, which can, in these electrochemical systems, produce a lot of chlorine. So that is something that research is figuring out how to overcome, because that can cause certain certain issues if there's other contaminants involved. But a lot of interesting ways to prevent saltwater intrusion and changing the groundwater quality through that path has been done using electrochemical systems.
Thank you. And also in your introduction, you mentioned that besides being a researcher at Northeastern, that you're also the chief science officer at another institution. Could you just tell us a little bit about that?
Thank you. Yeah, that's actually the next slide from this, but I just stopped. So I recently joined a couple of months ago at that position with a nonprofit organization in Western Massachusetts, and it actually spun off my great will to make some change in increasing diversity in STEM fields and how we approach the education in sciences. So what we do as a institute there is implementing different kinds of projects towards that goal. One is that you probably know that nonprofits usually suffer from a lot of issues with grants and donations and how you get funded. So our model is a little bit different, where we will have a coral farm that will be for wholesale of corals, and for, as well as researchers who are doing any coral-related research, where that will fuel our other projects towards education of high school students, middle schoolers, hopefully soon as well, where we will help teachers how to redesign their curriculums and how they can implement science projects in a better way so that students can grasp and engage a little bit more in sciences, because STEM fields really suffer from lack of diversity. There are a couple of conferences that I went as a woman engineer, and I was the only one sometimes. Or there were 5 of us versus 30 others. So I think there is a lot of need for that, and starting at the early age. So that was the motivation where we started this nonprofit organization to increase that participation and engagement in STEM. Thank you.
Thank you so much. Thank you so much for being here with us today.